Just now we just finished the Hall effect. So now we cover the circulating charge particle. And actually, in the last hour, I already show you the software demo that you can use some E field and B field, and then actually only B field, and then uh, and then the charge will actually have a circular movement, perfect circular movement, as long as the B field is uniform, as long as the E field is uniform, and the initial velocity of the charge is perpendicular to the B field. So a beam of electron is projected into a chamber by an electron gun. The electron enter the page with the speed v and then moving, and then it will have a Lorentz force Fb continuously deflect the electron, and because v and b are always perpendicular to each other, this deflect causes the electron to follow a circular path. The path is visible into the photon. Because this atom of gas in the chamber emits light when some of the circulating electrons collide with them. So actually, the argument here is that, for example, the charge is here, and then the speed is perpendicular to the b. So v cos b like this, and then you point to this side. If it is here, so v is point to this side, and then v cos b point to v cos b point to this side, and then you point to the center of the circle. So it's a circular movement. Actually, this is an argument based on the circular movement. And last year, I asked the student to use some differential equation to really find the locus of it. And actually, it is not really difficult. Not really difficult. But here, so we apply Newton's second law of the circular motion. We can have QVB is the Lorentz force F, and then A is V squared over R. If you can still remember the circular movement. So the acceleration should be V squared over R. So we substitute it here, F equals ma, and then F is the Lorentz force. This is the circular movement of the acceleration of the circular movement. So V and V can be cancelled. And then finally, R would be mv over qb, And then take the square root of q, so that this is a positive amount. So this radius is related to the mass of the electron, 9.11 times 10 to minus 31, and the velocity, the charge is 1.6 times 10 to minus 19 coulomb, and then b. So with a larger velocity, the radius will be larger. And then with a larger magnetic field, the radius will be smaller because the force is larger. So try to deflect the electron more severely, so that the radius will become smaller. So it is very simple, I think. Any questions? Okay, so here there is a sample problem. So an electron with kinetic energy 22.5 eV moving into a region of a uniform magnetic field. 4.55 times 10 to minus 4 Tesla. The angle between the direction b and the electron velocity is 65.5 degrees. What is the pitch of the helix path taken by the electron? So here, actually the velocity is not perfectly perpendicular to the B field. So actually we can decompose the velocity into two directions. One is parallel to the B field, and then other one is perpendicular to the B field. So for this component, this one, this V perpendicular component with the B will make the particle going into circular movement. And then for this one will just like a uniform movement, uniform speed, uniform velocity movement. So it will look like this. So if you just see it from top to bottom, it will have a cross-section circle. And then if you just see it on the side, you will see it will look like this, going from. So you can just decompose it the velocity. So you will try to going up, but actually you're going in a circle way in the horizontal plane. So overall, it will become a helix, 螺旋形的. And then the gap between the helix is called a pitch. It's somehow like this. So you get the exact same point, and then this is called a pitch. Don't try to find here, find like this. You should find directly horizontal, vertical line parallel to the central axis, and then this is called I'm not drawing very well, but actually you should find the point. Maybe you can find here and then here, and then their vertical position. Or if you can find here and here, then this is what we call the pitch. So here, we first also find the velocity, which is k over 2m quantity square root, not 2m, 2k over m. So which is 2k is 22.5 times 10, 1.6 times 10 to minus 19. So we convert the EV into joule, and then this is an electron, so the mass should be 9.11 times 10 to minus 31. Take the square root. So this one should be V. Should be V. So it should be 2.81 times 10 to 6 meter per second. 2.1 times 10 to 6. So next, we have the pitch. The pitch should be V parallel times T. So V parallel should be V cosine phi. Because this one is phi, so V parallel should be V times cosine phi. So this is the first term, and then the T should be 2 pi m over QB. So we substitute all the number into it, 2.81 times 10 to 6, and then cosine 65.5 degree, and then times 2 pi, and then m is 9.11 times 10 to minus 31. And then Q is 1.6 times 10 to minus 19. And then B is 4.55 times 10 to minus 4. So finally, pitch should be 9.16 centimeter. So actually this one, you can find the formula in circular movement, I think. Or actually you can find some relationship between this one and that one. So we can see V, QB, QB, QBM, QBM. So we just remove V and then put 2 pi there. Actually, if you can write out the differential equation, then you can be able to find this one by yourself. Actually, this one is not really sure I can do it now. Dx, well, yeah, yeah. So actually, this QVB equals A is second derivative of the x. Or we can just simply write this term as x double dot. Actually, this is not a good. There's no x here, so it is not a very good one.
We can change B to R omega, and then omega equals to 2030.
Oh, you're right. But actually, that may be a bit difficult to do it, right? Because actually we need to do something like the vector decomposition to other stuff. Maybe you can still you can only remember that one. So we have another sample problem. The essential of the mass spectrometer, which can be used to measure the mass of an ion. Mass M, and the charge Q is produced in the source S. So here is the source. You try to emit a charge, and then there is a slit, so that if it is go vertically up, so it will enter this chamber, enter this spectrometer. And then within this spectrometer, there are some B field pointing out of the page, which is perpendicular to the speed. So it will have a circular motion, but for half a circle. So finally, it will shoot on this screen. So it can detect what is the position of this charge shoot on it. Because if it is shoot on here, maybe there will be some light generated. So you can see the charge finally hit this point, and then this x will be double the radius, and then through this radius we can calculate the m over q, because if we just give a fixed b and then r is half of x, And then the V we should know that. Okay. So a wider detector, the semicircle does strike the detector, and suppose B is something like this, and that the V is 1000 volt, Q is 1.6 times 10 to the 9 coulomb, and then X is 1.6 something meter. What is the mass of the individual ion given blah blah blah? So yeah. So well, so maybe we can just do some calculation here. So actually first, yeah. So actually we have delta K plus delta U equals 0. We assume there are no loss for the mechanical energy. So 1/2 mv square, 1/2 mv square minus qv equals 0, which means that this is ground, this is ground, this is V. So there are some E field generated in this region. So that it try to accelerate this particle up to this point, up to this point. So here we have QV, which is the electric potential energy at this point, and all the electric potential energy will convert to the kinetic energy of the particle. So we make this statement. So we will get the initial speed at this point v. This is v. So v will be 2qv over m. Then take the square root. Take the square root. So this is v, the initial velocity. So next, as long as we have r equals mv over qb. And then we have v m over qb, and then in the previous line we have v equals 2qv over m quantity square root. So some of it can be cancelled, some of it can be cancelled. So it finally becomes 1 over b times square root 2mv and then over q. Oops. Because half of the q can be cancelled, half of the m can be cancelled. So they just swap. So, and actually x equals 2r. X equals 2r. X equals 2r. So finally it becomes 2 over b and then square root 2mv over q. So finally we have m equals x squared b squared and then multiply by q over hv. So we just multiply this one and this one to the right, to the left side, and then we divide this one, and this one to the left side, and then take the square on both sides. So m equals x squared b squared q, x squared b squared q over 8v. And then we substitute all the number into here. So we have x equals 1.6254, and then times b equals 80 millitesla. And then we have Q is 1.6022 times 10 to minus 9. Oh, these two need to be squared. And then over 8V. V is 1000 volt. 1000 volts. So finally, mass should be 3.386 times 10 to minus 25 kilogram, which is 203.93 U. 203.93 U, which is there are approximately 204 proton or neutron. So actually you can just check on the periodic table and then you can find which one is this particle. So any questions? So next we talk about the cyclotron, which is a particle accelerator. 这个中文叫做回旋加速器。So a cyclotron, the figure is a top view of the region of a cyclotron in which the particle proton stays circular. The two hollow D-shaped object, each open is straight edge for the blah 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 blah. So actually, let me try to explain. Yeah, actually, there are some. Yeah. So there are two disks, two semi-circle disks, but we try to separate a bit, and then we will have a E field alternating at this edge. But out of this edge, there are uniform B field. So in this case, if we just ignore this gap, as long as we have perpendicular B field with the particle, then you have circular movement, right? But now we just make some changes. So now we just make it like this. So in the middle, we have a small gap. So at the very beginning, it points to the left side, the velocity. And then the B field is pointing outside, out of the page. B field, uniform B field out of the page. So as you can see, this is a, well, I'm not sure. Yeah, it may be a proton, which is a positive charge. So B cross B, yeah, so pointing to the upward, right? So V is to the left side, and then B point to out of the page. So V cross B point to the upward. So this is the Lorentz force. In this case, we will try to move it like this for a semicircle. So in this area and that area, this area also we have B on this side and on that side. But in the middle, this is different. We have alternating E field. So we can just assume when the particle move to this point, we make the E field point to this side. We make the E field point to this side. So it will try to accelerate. So at this point, and will accelerate. So this one will be faster. This one will be slower. And then go to this point, and as the velocity become larger, so the R will also become larger. So it will try to go this way. Maybe I draw, yeah, maybe good enough. So this R will become larger. This R smaller, R1 smaller. So this R2 become larger. So now we change the E view to the left side. So it is an alternative E view. So go to here, and then so this is slower, although this is fast for this case. So this is fast. Oh. This is fast. So at this point, this is even faster. So it will accelerate, and then we will have another semicircle going to this point, and then E point to the right side. So it will further accelerate. So it's somehow like so it's called the cyclotron, 回旋加速器. So as long as we try to manipulate this frequency of changing the direction of the E field, we could make the particle become faster and faster. If we randomly pick a frequency of changing the E field, maybe it's not good enough because maybe it move here, and then the E field point to this side, or part of it point to the left side, then it will decelerate rather than accelerate. So we need to make this frequency accurate enough so that this cyclotron can accelerate the particle to a high kinetic energy. But actually, this one has a limitation. It can only accelerate the particle less than 50 mega eV. Because there are some limitation is that this disk should be very large. Which means that we need to have a uniform B field over this disk. And this is not a very good way to make a large B field over a large area, because we have a large amount of energy. As long as you have learned it in, I'm not sure. You have not learned it yet. In chapter 20, in chapter 30, you know the energy stored in a B field. But actually, as long as we need to generate a B field for some area, we need some energy. So if the area become larger, or the volume become larger, then we need to have proportional energy to supply. So which means that as long as we need to have a large velocity, and then this R would also become larger. Otherwise, we need to increase the B field. So this limits the energy for the cyclotron to up to 50 mega eV. But this is already quite good. So the next one is called a synchrotron, which is even more complicated. So we don't really have a figure to show how it really works. But actually, the point here is that the magnetic field B And the oscillating frequency, instead of having fixed value as a conventional cyclotron, are made to vary with time during the accelerating cycle. When this is done properly, the frequency of the circulating proton remain in step with the oscillating at all time, and the proton follow the circular, not a spiral, path. Thus, the magnetic need to extend only along the circular path. So in this case, this is only a ring. This is only a ring, so that we can provide a larger B field in this ring rather than a whole disk. However, this needs to be more concisely controlled because we need to fix the R, which means that if the V become larger and larger, we also need to make the B increase synchronous to this velocity. Otherwise, you may hit the wall, and then it will die out. So we need to make perfect control to make the particle accelerate. But here we only need a ring so that we can provide a larger B field at this region. So the magnet need extend only along the circular path, not over some 4 times 10 to 6 meters squared, which is really large. You can imagine it is 2 times 10 to 3rd meter, which is 2 kilometer. 2 kilometer. So you can imagine the radius of this one is 1 kilometer. 1 kilometer. So the circular path, however, still must be large if high energy are to be achieved. So in Wikipedia, we can check the proton synchrotron. The beam is then injected into proton synchrotron booster with accelerate the proton to 1.4 GeV, followed by the proton synchrotron. We push the beam to 25 GeV. So compared to this one, we can have a 100 times larger, yeah, 500 times larger energy. But what does it use for? What does it use for? So maybe we can check back. Chapter 21. I have introduced the standard model of the elementary particle. So the physicians want to find the elementary particle rather than just the proton, neutron, and electron. So they try to break this one into smaller pieces. So 你可以想象啊，就是如果你要把手机拆开的话，你要怎么办？就是你可能拿个工具把它拆开嘛，但是这很花时间，而且拆的效果也不好。那最坏的效果就是说你拿起来一手夹到地上，然后它就爆开，那就是最快的。那所以为什么要粒子加速的话，就是说他们希望把那个速度加得很快，然后让粒子对撞之后，然后它就会炸开，希望它能够炸出一些比较更小的一些粒子出来。So you can check here, yeah. So in this table, you can check there are some mass here. So for generating the first generation, we need 2.2 mega eV, 4.7 mega eV. But here we need 1.28 giga eV per C meter to really generate these quarks. And for these two, we need 173.1 giga eV per C squared to really generate them. So that's why they want to have a particle accelerator. And a few years ago, the physician claims that they can generate the Higgs boson. 就是前几年前说的那个上帝粒子啊，上帝粒子就是需要这么大的能量才能够把它产生出来。那它是一个很奇怪的东西，就是说，这个很奇怪，就是说，他们说其他的粒子啊，它们的质量是由这个希格斯玻色子来赋予的，所以它就有一种类似上帝的那种能力，就是由它赋予其他粒子它透过它们之间的交互作用来把那个质量交给其他的粒子，所以很奇怪，我也不知道是什么玩意儿。So let's come back. Okay, so this is the synchrotron. Okay, so let's see in sample problem. So suppose a cyclotron is operated at an oscillating frequency 12 megahertz and the D has a D radius R equals 35 centimeter. What is the magnitude of the magnetic field for the deuteratron, one proton and one neutron? So this is a type of hydrogen, but with one more neutron. So to be accelerated in the cyclotron, the deuteratron mass is 3.34 times 10 to minus 27 kilogram. So actually we can use this equation. F equals QB over 2 pi m. F equals 2. So actually we can just rearrange it so that we have B equals 2 pi m F oscillation over Q. So we substitute 2 pi and then m is 3.34 times 10 to minus 27, and then frequency is 12 megahertz, 12 times 10 to 6 over Q. Q is one proton, one charge, one elementary charge, 1.6 times 10 to because the one is proton, which is plus E. So this one without charge. So we only have Q equals to E. So B is 1.57 Tesla. So which is not really huge. But maybe it's quite big. So for B, what is the resulting kinetic energy of the deuteratron? So we can use V equals R QB over M. So because we have R equals mv over QB just now, so we can just rearrange the term so that we have V equals R QB over M. So R is 53 centimeter, 0.35 meter, and then Q is 1.6 times 10 to minus 19, and then B is 1.57 Tesla, and then M is 3.34 times 10 to minus 27. So the V would be 3.99 times 10 to 7 meter per second, and then the kinetic energy will be 1/2 mv squared. So 1/2 times 3.34 times 10 to minus 27 times 3.99 times 10 to 7 quantity squared. So it will be 2.7 times 10 to minus 12 joule, which is 17 mega eV. So you just need to divide this one by 1.6 times 10 to minus 19, that will become 17 mega eV. Okay, so yeah. So next we talk about the magnetic force on a current carrying wire. Current carrying wire. Okay, so now we consider there is a wire. There's a wire. So without any charge, even with a magnetic field, there will be no force acting on this wire, right? So if there are some current maybe going to the from bottom to top, then there will be a force acting on this wire. We try to fix this on the bottom and top, and there will be a force acting to the right side and the force acting to the left side. So we can imagine if there are current going from the bottom to top, there are some electron moving from the top to bottom. So this is the V, and then the B is pointing to the outside. So V pointing to the bottom, and then B pointing to the out of the page. So V cos B point to the left side, and charge is negative. So the Coulomb, the Lorentz force point to the right side. So FB point to the right side. So you can imagine like this: if the current is going from the top to bottom, then FB should point to the left side. FB should point to the left side. And actually, we can calculate it like this. So actually, it's somehow like FBQ QVB. QVB. FB is actually QVB, but now we have many charges. This is for single electron. Now we consider a current. There are many charge, so we have I, and then V going for this length. So we have L and B. So actually, you can do some change of variable. You can derive it from the Lorentz force to this one, because I is somehow like dq dt, yeah. And V is L over maybe L over, so I dt, so V dt is actually, so we have Q is dq, so now dq would be I dt. So dt multiply this V would be the dl. So actually there's the total Q and the total length. So now it becomes I times L. And actually the direction should be V cos B, and here is L cross B. L cross B. Because this is electron, this is current, so you can already provide the negative sign. So here we consider the current direction, which is L cross B. So now we can consider the I pointing to the upward, so L point to upward, and B point to the out of the page. So L cross B point to the right side. L cross B point to the right side. Here, L point to the lower direction, and then B point to the out of the page. So FB point to the left side. So we can. So L is the length vector that has the magnitude L, which is the length of the wire, and then the direct along the wire segment in the direction of the current. Okay. So for this case, L point to upward. For this one, L point to the okay. So any questions? So actually, we can just make it a. If it is not a uniform B view, we can just cut it into many small parts, so that we can use the integration to calculate the overall forces due to the magnetic field or due to the magnetic field to a wire. So maybe we just stop here, and then I'll see you next week. Okay.